Okay, I'm going to accept that. So Cybers has documentation, which is hosted over our Learning Center. So the URL is learning.cybers.org. And we have information here about getting started with the platform, who we are, why we're here. And just to explain, so Cybers has been around for about 13 years. It started out as the iPlant Collaborative, and it was funded through the National Science Foundation's Biological Sciences Directorate. And the purpose of Cybers, or excuse me, at the time, it was actually called the iPlant Collaborative. The iPlant Collaborative was focused only on plant sciences. So it was a cyber infrastructure which was established for plant scientists, mostly to do genomics work. And in 2010, the cyber infrastructure was released publicly for users to sign up. And over the next 3 years, we gained a large number of folks coming in to use the platform. We had, at the time, a data science workbench called the Discovery Environment, which you guys are going to use in a few minutes. And the DE is attached to our data store, which is an iRods managed platform. And I'll try to explain iRods a little bit later, but all these things come together to offer Cybers as this featured product. We had other services which we incorporated, including things like the BISC imaging platform and another platform that Edwin's team built called Atmosphere, which we'll also be using today, which is now called Jetstream, and it's actually called Jetstream 2 because it's in the second funding cycle. But those are OpenStack cloud-based instances. And so to think about Cybers is a little complex. It was called the iPlant Collaborative for the first 8 years. It changed its name in 2016 to reflect the new broadened direction from NSF, which was to serve all life sciences. And in fact, we serve more than just the life sciences now. So my background here has a rocket and space on one side. So that's to reflect the fact that we're actually helping Earth sciences community and the space sciences community. So there are many different science domains now that are using Cybers to do their science. And our background is in plant sciences. That's our first and our primary focus. But Cybers has been many different things, and it continues to evolve as this data science landscape changes around us. So I'll go back and get my Chrome up here again. So if you're interested, you can come in here to the Learning Center and you can go through the documentation. You can learn more about how our data storage works. I'm going to spend a lot of time in the next hour talking about our data storage and our data science workbench. We are going to be working on our OpenStack cloud also pretty soon. And if you're thinking about incorporating Cybers outside of this IRA or in Coalesce project, you would look into some of these things like our external collaborative partnerships. There's also a self-guided tour, which is a kind of a MOOC. It's a massive online classroom where you can come and self-paced learn how to use the different tools that we have. We have videos here for you to explore if you want to do that. Okay, so let's do it. Let me check the chat real quick. Let's see messages. So let's go ahead and click on this link that will take us to the discovery environment, or the de.cybers.org. And I'm going to put this into the chat. If I can find chat. So for most users, the first thing that they're going to see when they log into Cybers, well, excuse me, you can go to the user portal. So the user portal is sort of like our Grand Central Station. So this is user.cybers.org. This is where you guys came after you signed up your accounts. And you'll have this list of services. And so you can request access to these different services. For anyone that doesn't have access to Vice yet, you need to click on this down here in your available section to get access to it. So as a new user, you likely only have access to the discovery environment. I've been a user of Cybers for a long time, so I have access to most of our services, but actually not all of them. So we can click on the DE button. So this de.cybers.org is our data science workbench. I'm going to log out and I'll log back in just so you guys can see this. So when you first arrive here, you can still see the workbench. You can see some videos, some featured apps that we have. In the upper left side, there's these 3 bars. We call this the hamburger menu. So you can click on this and it'll open up the tab, and you can see the different features that we have in here. So we have the data, which will be access to the data store. We have apps, and within apps, we have this concept of tools, and then the instant launches is a way to launch an app in a single click. But you can launch jobs and interactive development environments from the apps feature. And then once your apps are running, they show up in your analyses. We have a quick launch button here for the Cloud Shell if you want to just jump into a Cloud Shell instance, which is a terminal in about 30 seconds. We'll go over this concept of teams and collections a little bit. But also importantly is this help button. So if you need help, you can click here and you can see that there's some lists that will connect you back out to places like our Learning Center or our product guides. Currently, I'm not logged in, so I can click on the Chat with Cybers button, and this will open up a intercom messaging service. So you can type a chat message to us. This is a Saturday, so normally our team aren't working on the weekend. Typically, if you contact us during the week, we'll be online and we can try to get a response to you within as little as 15 minutes. So we try to talk to our users and help them get through their problems as fast as possible. Okay, so I'm going to go back to this home feature. So you come to the DE, you're in the dashboard, and you can click here to log in. I believe if I click on my icon up here, it'll also take me to log in. So this is our Keycloak login screen, and my browser has saved my username and password. The cool thing about Keycloak is that you can federate your Cybers account with your institution, with your GitHub account, with your Google account. So you can log in using any of those other services after you've set that up with Keycloak. So I've clicked log in, and so now I've just logged into the discovery environment, and the screen has changed a little bit. We have some kind of information about if you want to take a survey for us. This new feature here is actually not totally active yet, but it's a resource usage. So you can currently access Cybers completely for free, but we're going to be transitioning our platform to a sustainable model in the next 2 years. And so this is kind of pre-staged for when that finally kicks off. But I can see how much data I have in my data store. Obviously, I'm over quota right now. So if I'm set up as a basic tier and I'm using 7.8 terabytes of data, but I only have 100 gig allocation, it shows me it's being over. I've used about 5,000 CPU hours in this last month, so I'm also over on that. But then I can see the stats of how my jobs have run. So there's just some kind of quick launches here where if I want to go and look at analyses that I've run. So I've actually got a Jupyter lab running right now. I completed these other analyses a few days ago. And if I want, I can quick launch any of these instant launch features by just pressing the launch button. There's also the other ones that have been launched if I want to go and relaunch those. So we're not quite ready to launch an app yet. You guys can go ahead and launch one if you want, but we'll have to cancel those out and restart them when we're ready. So the concept here is that the discovery environment is a one-stop place where you can come and you can do your research. You can load your data into the data store. And so we saw that I have like 7 terabytes, 8 terabytes of data in my personal space here. So in each of these project folders, I've got data sets that I've saved, and I'm sharing these out with my community members. If you click on the home icon, which shows your username, you can see that there's 3 different options. So you can look in your account, you can look in this shared with me account. So this will show you any other files from any other users in Cybers that are shared publicly or are shared privately with you. And so I'll talk a little bit more about the concept of file sharing in here, but we're using Linux. And so we have conventional Linux file permissions on all of our files and folders. In your personal space, you have private folders. So I'm going to go ahead and create a folder right now. So I'm going to create this folder. I'm going to call it TrAC Train 2022. And I'm going to use just a normal Linux file path. I'm not going to put any spaces in this file name. So because we're running on Linux, we do not want to have a space in our file name. It causes problems. You can use things like snake case or camel case if you want, but I'm going to keep my file all together. I'm going to use lowercase, and I'll do the date. So I'll say create. And so this will create a new folder on our data store. So the iRods data store is essentially like what you hear on things like Amazon Web Services as being like S3 or a data lake. So this is a cloud-based data storage platform. Because we're running iRods on top of it, iRods stands for the Integrated Rule-Oriented Decision System. The iRods adds in additional metadata and file tracking such that we can make all of the files in the data store searchable. So up here at the top of the discovery environment, there's a search bar, and I can search doing a basic search or even advanced search to look for data in the data store. These data can also be shared publicly with the internet. And once they're shared publicly, those metadata are exposed to search engines using schema.org. So if you add metadata to a folder, you can then share it publicly with the internet and Google will find it. So those are things that a normal cloud bucket won't do for you. So I've got this new folder that I created. I can look inside of it. There's nothing in here. I can create a new file in here. And if I want, I can give it a name. So I'll go ahead and create a what's called a markdown file. And I'll say create. And so when this comes up, I can give it a markdown syntax. And I can see how it's rendering as a file here. I can give it a URL real quick. Let's do this. We'll copy in our schedule. Lost my tab. Okay, so I'm going to put in the URL. And we see that it renders just as markdown. So I'm going to save this file. I'm going to name it readme.md. And it's going to save it into this new folder I created. Okay, so it's saved. I'm notified that the file saved successfully. I can come back and I can see that there's this file here now. I want to do, well, let's go ahead and do a share. So there's the concept of your personal user path, which is private to you, only you can see it. And you can click on the folder to select it, and you can share it. And so we have this sharing menu where I can share this with other users. So I can find Aditya, and I can share this file that I created with only him. So he can read this file. I can give him edit ownership over it, or I can give him ownership of it. So if he has right ownership over that file, he can edit it, but he may not be able to delete it necessarily. If he owns it, he can delete it, and he can remove me as the owner of it. So we always want to be careful about giving different file permissions to files to other people on the internet. But specific in your personal space, this is one way that you can share your data sets. We created let's see if I can find this, a team for this workshop called TrAC Train. Oh, I apparently can't, I forgot, I can't save data yet. I can only save, share apps with this, but I can share this with the public Cybers user. And so if I share with public, this is now available to anyone with a Cybers account. So now I'm going to go ahead and say done. And it's going to share this file. I should get a little update here in a second and set it's shared. So now anyone in Cybers, if you guys go into your shared with me folder and you scroll down to T Swetnam, you should be able to see the TrAC Train folder, and you should be able to see this file that I just created. So you can share files within the discovery environment with your community members. You can share them with anyone on Cybers. You can also share it with the internet. So if you want to share this file publicly, you can add the anonymous user. So the anonymous user is the public internet. And I'll explain how this works in just a second. So I'll share this. And so this file permission has now just been opened up to anyone who wants to look at this on the internet. I'm gonna log out. Make sure I close all my other discovery environment windows that are open. So I'm logged out. I can actually go to data, and I can go to, see if I can go to the shared with me. I can only sign in to see it. Yeah, and you can't see it from the discovery environment. So the file's public. We can't see it from the public interface. But if I come to this URL, so I'm going to go to data.cybers.org. This is our public endpoint running what's called a WebDAV service. And WebDAV is, you can go read about WebDAV online, but it's a way of exposing the iRODS data store publicly to the internet. So we're using a cloud bucket type architecture, but this makes it look like it's coming to you over a website. So it uses the HTTPS protocol. And we have our community release folders. So we're going to be spending some time working in the community release folders a little bit later in the Soinomics folder. So we can see that Aditya has created a folder that we're going to look at a little bit later. But we can go to the projects folder. I'm going to have to log in here. So you see, I don't want to do projects. I want to do home. So I'm going to go to iPlant home, my username, TrAC Train 2022. And if I look in this folder, I can see now this public file that I released. And this is looking at data.cybers.org over the anonymous WebDAV. So this file has just been published out to the internet. Anyone can see it, anyone can use it. You can download this file using things like curl commands or wget commands. I'll show you another example. So it doesn't have to be just a simple file. It can be even HTML. So you can actually publish PDFs or web pages through here. So I have in this leaflet example, actually let's go to, yeah, we'll do this one I guess for now. So I can click on my map, HTML. And then this is going to show me a map. So this is running through the WebDAV, and it's loading data sets that are there in the data store, and it's just a URL. So you can publish your data. You can publish things like R markdowns or PDFs using the file sharing permissions through the data store. And if you want to share or look at private files, you can go to the full WebDAV, which is going to ask me to log in. So if I click on the home folder now, it's asking me for my login. and I authenticate my Cybers account through the browser. Oh, it's trying to read the whole data store right now. So let's try to get into a smaller folder there. So if I can now log in privately to that same public folder. I can go to a folder that has both private and public data in it, and I can view those through an authenticated mechanism. So you can share your files over HTTPS, both privately and publicly. I'm going to share my whole desktop now. And I'm going to open, let's see. Can you guys see CyberDuck? Can't see you guys. Is there a thumbs up anywhere?
Yeah.
Okay.
Yes.
So I've opened CyberDuck on my Mac. CyberDuck is available to Windows users and Mac users only. But you can sign up with Cybers, get your Cybers account, and then you can download the Cybers profile. And you can then log into the DE using CyberDuck. So I double tap on this, and then it reads through my file tree, and I can view my files. I can upload and download these. So the benefit of having CyberDuck is that it's not based out of a browser. So when you try to upload or download files through the browser, you're typically limited to a maximum of about 2 gigabytes. I believe that's the maximum size of an HTTPS protocol file. So with CyberDuck, you can move larger files up to any size. You just drag and drop them in here, and it'll upload or download to the data store. This is for moving data from your laptop up to Cybers. I like CyberDuck because you can connect it to just about any platform that's out there. You can use it FTP, you can use SFTP, WebDAV. All of the large cloud storage providers are here, so you can connect to your S3 buckets. You can connect to your Dropbox or your Google Drive. And so it's a nice way for you to move files down to your laptop. It's a little different when we get into working on the cloud and we don't want to download things, we just want to move them around the cloud. But if you want to move files up and down, CyberDuck is a good way to do that. I'm going to open up my Finder. And so let's see, I'll go to Finder. I'm going to go to, where's my new connections? Maybe I have to do a plus down here. Go. Okay, so if you have a Mac, you can go to your File Explorer. I'm going to connect using the WebDAV to my Cybers account. I have to put in my username. Okay, so now I'm going to change this view. So now I'm connected back to Cybers using my file manager on my laptop. You can do this on Windows or on Linux. So you can connect to the data store this way, and you can drag and drop files using this. So this is just another way that you can move your files up and down from the data store. And I'm hoping that some of you guys are kind of following along and trying to do this on your own. So we've got these different ways of moving files to and from the data store through the browser, through CyberDuck, or through even your Finder. Yeah, and Yash asks about FileZilla. Yes, you can connect and move with FileZilla as well. So we have all these different ways that we can move data to and from the data store. We can think of the data store as being independent of the discovery environment. So if you wanted to just put data on Cybers, you can just use the data store. The discovery environment is a useful tool for viewing your data and for sharing your data, but it's not necessarily required. Okay, so Nirmal, you're asking about from the data store portal. So you can go to your home. Let me sign back in here. Okay, so you can only see this. So if you click on, I'll come down here, go into TrAC train, I click on the file, so you can see the share option, the refresh. So you can click on more actions, and that'll show you a few more things. But the share should be either be in here or it could be exposed here. This menu collapses. So if I reduce the size of my browser, things will get moved into this three dots for the more actions. So I just want to show real quick that you can annotate things with metadata. And so this new file I created has a little bit of metadata associated with it, but I can either add metadata by creating new attribute value units, or I can click on the more actions and I can add metadata using a template. And so if I want, I can apply something like the Dublin Core metadata template to this file. And this is the template. So when the template comes up, it'll show me a title, a subject, description, rights, creator, etc. And so you can annotate your files or your folders. Each one can be annotated separately with metadata. You can create your own metadata. So whatever kind of metadata you want, you can add to this file or to this folder. So you can annotate with metadata. These things would be searched by a search engine. The only way that you can then view those metadata is if you come in back to the discovery environment, but the community data, which are in public folders, like the Soinomics folder down here. So if I go to community data and I scroll down to Soinomics, we can view its metadata. And we can see that there are some metadata which have been already applied to this. These metadata are visible when we come to the Cyverse Data Commons, which is just a forward-facing web page for seeing data sets that are in Cyverse. So the data commons have two types of data: community released, which are living data sets, which can be edited and changed by their owners, and curated. Curated data sets are data sets that have been published and have been given a digital object identifier or a DOI. These data are immutable. So they've lost their write or edit permissions forever, and they're permanent data types. So before we can publish a data set with Cyverse, the users have to apply all of the relevant metadata that are required for a published piece of data. And so we review those, and then we let them be published with DOI. So this one here has a DOI, it has the creator, the description, the publisher, etc. So these are the required metadata that a file needs in order for it to become public. The community data sets, let's get out of here, are still visible. So I'll scroll down to the Soinomics file down here. And when I view the Soinomics folder, I can see these same metadata that we can see here in the discovery environment. But because I'm a member and an owner of this, I have edit permission over these. So if we wanted to add more metadata to the Soinomics folder, we can still do this. It's not too late. If I click into the TrAC train folder, notice how the metadata disappear. So this folder that we're going to be using today for our demonstrations doesn't have any metadata applied to it yet. So it's okay if a folder has metadata or doesn't have metadata. It's only necessary if you want to move towards publishing that data set as part of your research. Okay, how are we doing on time? We're still got lots of time. So I want to talk about another way that we can move files around the data store. So this is going to require us opening and running one of our visual interactive compute environments. And so this is going to be kind of a big step for us. what I want everyone to do is to log into the discovery environment, and then I want you to come to the instant launches. And under the instant launches, I want you to find a Jupyter Lab Data Science Latest, and I want you to click on it. And so when you click on that link, and I'll put this into the chat. So when you click on the link, it's going to trigger Cybers to give you a virtual machine. And for some of you, you're going to get rejected from this because you didn't sign up for Vice, and we don't have access for you yet. So we'll have to do that. But I want to wait a few minutes and let's get this running for everyone. I'm going to see if I can help get people approved right now as they fail. And I'm going to see if I can bring up my screen so I can see everyone in gallery view. So what I would like right now, let me see if I can stop and reshare my screen so you can see what's happening. So my app is starting right now. You guys up to another monitor here. Hold on a second. Yeah, it won't let you guys go to another monitor. Okay, so as you guys get access, either chime in the chat or just give me a thumbs up. Okay, so Khan is asking how to sign up for Vice, and Masu's got an error. This is what I was waiting for. Okay, so what I think I need to do is, if you guys don't have access to Vice, we can try to send you a link to get you access. I'm going to check for Vice approvals right now. Okay, I see Zubin has got access now. Devish, you're going to have access now. Ping Lang, you're going to have access now. Okay, let's see if I can go to the user.cybers.org. I'm going to copy a link right now for you guys. I'm going to put this into the chat. So for those of you that are getting error messages, I presume that if you click on that URL, services 43, there's going to be something in there about requesting access to Vice. Okay, so my Vice instance has started, but I want to wait until everyone else gets in here. Just for anyone that's still requesting access, just put TrAC train 2022. Okay. Chats and keep approving people. So I'm approving everyone with our default number of Vice instances, which is 2. So you guys should be able to start up to 2 virtual machines concurrently. Okay, so I've just approved everyone that's clicked in the last couple minutes. And I'll walk through this again. So from the DE, you open the tab and then you look under apps and you can click instant launches and you can click on data science and it should launch your app right away. And then once the analysis is running, it should take you directly to the Jupyter lab. But if you don't have that, you can look underneath analyses and you should see that your analyses is running in there. And if it's not there, you can try to refresh the screen. And so I have two of these running right now. I have a large PyTorch image running, and then I have this data science one. The PyTorch image is really big, and it's not cached on all of our nodes. And so it's going to take longer for us to get into those. So I wanted us to just drop into the data science one to demonstrate this iCommands exercise first. So to connect to your Jupyter lab, so I'm going to close my other tabs that I have open here. So I can either click right on this analyses for data science, and it should reopen the tab. And it logs me in. And so it should pop open a new tab whenever you do this. And you'll see the URL of the new virtual machine that you're running on inside of Cypress. And this is running a Jupyter Lab Docker container, which comes straight from the project Jupyter group. And it has a few extra things installed. And that's what we're going to go over here in the next few minutes. So let's see, what time is it right now? We still can't find my time. We got a few more minutes before our break. So you can connect to it either by clicking on the left side of the analysis tab, or over here on the right side, I can see a couple of little icons. So there's a view logs icon and there's a go to analysis icon. So if I click on the go to analysis icon, it will pop open another browser tab and it'll put me into the notebook. Okay, so I'm going to close this again just to show you one more way to open this. So you can see the analyses, you can click on it here and it'll open. Okay, let me check the chat one more time. Let me find my screen. Okay, I can see, I think all 30 of you guys on my screen, or 40 of you. Can I get thumbs up or thumbs down right now for whether or not you were able to successfully start a Jupyter lab in the DE? So there's still a few of you that are waiting. Can I have thumbs down for anyone that's still having problems that they cannot access the discovery environment? We've got 5 more minutes to work on this, and then we're going to go to a little bio break, and we'll come back and we're going to start using this a little bit more. So I'll have a few more minutes to get you guys in here. So it looks like there's still a few people that are waiting to get on. But I think we have enough time here for me to do this next step. Okay, so in my Jupyter lab, we have a couple of things that are visible here. Oops. You can see your launcher for the Jupyter lab, and specific to Cybers, we have some special things set up here. So in the working directory of our container, we have 2 folders that are visible. There's a home folder and a data folder. The way that we started this app, we didn't put any input data into this container when it started. So we're just putting the basic image up and it starts. if I look inside of the home folder, what I'll actually see is my username in this shared folder. Inside of the username is my data store. So these are all my private files that are in my account. So this container launches with what's called the container storage interface driver. And so it's essentially fuse mounted the cloud data store of Cyberse into my container as a path inside of this virtual machine. If I click on the shared folder, it's a little slow. Give it a second. Let me refresh this. Taking a while. I'll let it wait a minute. So the shared folder is trying to read through all of the public folders in Cyberse. There it goes. Oops, and I rebooted too many times. Okay, sorry, it took a second to read those. I'm not sure if that's just my home internet provider, if it takes everyone a minute to load that. So this is just loaded the shared folder, and I can click on the Soinomics folder, and I can click on our TrAC train folder, and I can see these same files that Aditya has for our demos that we're going to do a little bit later. So these files are visible here in this widget, but they're not necessarily on the VM. They're on a fuse mount on the VM. So they're not as fast as if they were on the root system of this, this Jupyter lab. So let me just explain what I'm about to do here. In the launcher for the Jupyter lab, you can click on terminal, and that will open a Linux terminal for you. And it puts you into the working folder of the container. So this folder is in the cd/home Jovian work path. So that's the full path of where I'm at right now. And what it can see are these two folders called data and home. And then these are mounted from the iPlant home path. So if I say cd home /T Swetnam, so that's my username, I can now see
Finder hasn't added support for that with C.
Siri was trying to talk to me, I'm sorry. So I can cd into my home user path, and I can see my files. If I cd back into the working directory of the container, I go all the way up into home Jovian. So I want to say cd work home shared, and I can then view all the public folders in Cyberse. So I can cd into Soinomics, and I can view the folders that are shared with me in Soinomics, and I can go into the TrAC train April 2022, and I can view the files that we're going to be working with. So these files are, there's a 2.7 gig file, a 564 megabyte file, an 11 gig file. So these are not small files, but they're visible here, and I should be able to open them and edit them. Using the fuse mount, though, can be a little dicey because you're expecting software to move your data for you. So we can move this file onto the virtual machine that we're actually working on. So I can put it actually onto the disk on this virtual machine, which will give me better performance. But we're at time for break. So I'm going to pause for the next 5 minutes, and we're going to come back at the top of the hour. And anyone that wants to unmute or say hi or turn on their camera, you're welcome to do that. And we'll get ready to move on to the next thing. The Google Docs. So each of you has been assigned to a node, and the way that you get to your node is to go to the URL TrAC train, and then 0, whichever number, or 11 or 12, whichever number you want to use. I'm going to drop into TrAC train 15 for right now for myself. So when I click on this, it's going to log me in using my GitHub username. This is not using Cybers. This is going to be using GitHub. So let me see if I can see you guys. So find your username on there. Let us know if you don't have your name assigned to a node or you don't see your name on the spreadsheet, and we'll get you invited to one of these virtual machines. And then give me a thumbs up after you've signed into the TrAC train node that you were assigned on and you drop into your Jupyter lab. And alternatively, give us a thumbs down or let us know in the chat what's going on. So people are getting in.
Can you show us again how to log into a specific node we're assigned to?
Yeah, so it should just be, let me see if I can open up the spreadsheet again. So you should look for your name on the spreadsheet, and you should see on the right side there, TrAC train, TrAC train, and then 2 numbers. If it's less than 10, it starts with a 0. And then if it's more than 10, it looks like there's a few names in here that haven't been assigned. So we need to get your GitHub username in here. So I can see folks in here that haven't provided a GitHub account. So we need those GitHub accounts so that we can assign you to one of these nodes, because we're using GitHub authentication on Jetstream today. So once you've found which node you're assigned to, in your browser, you type in TrAC train, the node that you're on. So let's say I'm on node 14 right now, .cyverse.org. And when you log into that the first time, it should ask you something like sign in with GitHub. And so then you'd use your GitHub to sign in. And it should start up a Jupyter Notebook for you.
Yeah, thank you. It's working.
Good. Okay, so what we're doing right now, so I kind of shot past the entire concept of Docker. Could you guys raise your hand if you know what a Docker container is? And if you do not know what a Docker container is, you can give me a red X or a thumbs down or some other kind of negative sign that you've never heard of this crazy thing called Docker. And it's totally okay if you've never seen Docker or used Docker before. Okay, this is good. So I'm going to take a couple minutes right now to explain what the hell Docker is and why it's important for us as scientists. So virtualization is not new. It's been around for a long time. But the concept of a container has become prevalent in the last, let's say, 8 years. And containers are a way of abstracting an operating system over a virtual service like the cloud. So it used to be that if you wanted to virtualize an operating system for testing or development, you would have the machine that you're working on. Let's say it's a workstation in your lab. You have hardware, you have a software kernel, and you have the operating system that is installed on the machine. You then have the software that you're using day to day, or you have the virtualization manager like VirtualBox running. And then VirtualBox runs another operating system on top of it. And then that runs the software in that operating system. That stack is very heavy because you're running multiple OSs just to get to your virtualized operating system. Docker runs against the software kernel actually underneath the operating system that you're using. So when we run Docker containers, the container is actually talking directly to the hardware and the kernel on the machine on which it's running. So this means that Docker can run software probably faster than the software that are running on your host operating system. And so by using Docker, we can create containers. And the concept of the container is just that it's a small, lightweight way of packaging an operating system and running them. Containers are now the dominant mechanism for using the cloud. And the reason is that you can go to Google or to Amazon or to Microsoft Azure, and you can request a virtual machine hardware resource. And if it has Docker pre-installed, you can immediately deploy your container. Our container is maintained on a public library called a registry. And the registry is just a bunch of images that are hosted by a service. And when the container is called by Docker, it downloads the image from the internet and it starts the container. So what we're doing in Cybers right now, or we're doing a few minutes ago, was using an infrastructure to start a container image, which I've got hosted on a registry. This virtual machine that you just started with a static URL on the Jetstream cloud is running a set of software on it with Docker to allow us to run the same Jupyter Lab container with the machine learning software we want to run today pre-installed. So the fact that you guys can click a button in Cybers and within 30 seconds be inside of a container with all of the libraries and packages you need is part of the justification for using software containers. We are moving past the step where you all have to build and compile and run software yourselves. We are hosting this container for you on the internet. So if you guys want to see this same container that we're running today, I have it here on GitHub. And the version that we were using just now in Cybers, the recipe file or Docker file for that container is visible here. So we're using an official image from the Jupyter project. I'm installing iCommands. I'm installing Go and Rust. There's actually a CyberDuck tool that's pre-installed in here. The GitHub command line tool is pre-installed in here. And then down here at the very bottom, we're installing PyTorch and MLflow and these other tools that we are going to use for the last half of this workshop when we actually do machine learning. So this container is like baked cookies. This recipe file is coming to us with the eggs and the sugar and the cream, and most importantly, the fancy milk chocolate for the machine learning that we want to do later on, and walnuts. So hopefully there's no raisins in here. The idea is that the container comes as a pre-baked tool for us to use. So we were using Cybers, which is a cyber infrastructure which manages containers for us. It also has a data store that we can keep our files on. We're now using this cloud to run our container. And the reason we're using this cloud instead of the Cybers data store is that if I type in NVIDIA SMI, which is their monitoring tool, I can see that this container comes to me with a GPU inside of it. So Jetstream is a brand new machine, and it has these A100 NVIDIA GPUs installed. For those of you that follow GPUs, A100s are or were the top of the line GPU that was released 2 years ago. That GPU cost probably $15,000 to purchase. So we are sharing virtual machines together. Each of us is on a virtual machine. There's 4 users inside of each of these machines. The reason why we're only doing 4 people in each machine is that we're sharing this GPU. So I get access to 1/4 of this GPU. I still get 10 gigabytes of memory. So that's enough for me to run the examples that we're going to do in the workshop today. If you were to get a full Jetstream node, you would get access to a full GPU. And so if I come here and I look at this, a full GPU is going to give me 32 cores, 125 gigs of RAM, and the full 40 cores of RAM on that node. So when I use Jetstream, I can scale up to a much larger scale than I can currently give you in the discovery environment. But for this workshop, we're splitting and we're sharing a resource so that we can all do this together with the GPU, which allows us to run CUDA, and it will process our training models orders of magnitude faster than if we were to try to run PyTorch on a CPU-only platform. So that was my overly long introduction to containers. I'll also point out that Cybers teaches Container Camp workshops. So for anyone that needs more introduction to containers, I'm going to drop this link into the chat. You are welcome to sign up for Cybers Container Camp and tell them that I told you to sign up and that you're from the IRA or Coalesce groups, and you heard about this in the TrAC train, and you want to learn more about containers. And so we'll have a virtual container camp in May that's going to be on basic containers, building and running containers. And then we'll have an advanced camp in Tucson for those of you that are interested in learning about using containers on high performance computing, on high throughput computing, on the Jetstream cloud. And then also how to build and deploy these containers using continuous integration and workflows. So you're welcome to attend those workshops. Okay, so we've gone through a little bit of the Jetstream 2 background. This Jetstream container that I'm running in, I went ahead and I used the iRods config to sign into Cybers. So I put in my username and password here. But we need to log back into iCommands because we're on a new virtual machine. So remember, I asked you guys to shut down your discovery environment virtual machines because we're not going to use them anymore. But we need to log back into iRods on the new machine. So on the TrAC train GPU VM, I'm going to type in init. And this time it asked me for my username first because these machines don't know who I am yet. So I'll type in my Cybers username and my Cybers password. And I should now be connected again to Cybers. I can connect through the widget over here, but remember this widget is not mounting the data or moving files around. It's just showing me the files in the data store. So if I want to use the data that Aditya's got for the workshop, I need to move them onto this Jetstream container. So I'm going to, just to do a shortcut, I'm going to log into the config. I'm going to scroll down to Soinomics. I'm going to sign into the TrAC train folder. Aditya, we're going to be using the tar.gz file, or the npz file is the one we want to use. We want them to download.
So we would be downloading both of them actually, the tar.gz and the npz both.
Okay, so let's do that. So I'm gonna copy the file path so that it's less for me to type. I want us to do a couple of things here though. So I'm gonna ls here in the container. I want to cd into the work folder. And then I'm going to create a new directory. So I'm going to say make dir TrAC train 2022. I'm going to cd into TrAC train 2022. Okay, so there's nothing in here. I'm now going to use the iCommands iget command to download these data into the virtual machine on Jetstream. So I'm going to say iget I'm going to use the K flag for checksum. We didn't do this yet. I'm going to use the -P flag for progressive output and the small v for semi-verbose output. And I'm going to paste in this tar.gz file. And I'm going to let it download. So this is 2.7 gigs. We'll see how long it takes. So this file is moving from Tucson to Indiana. And it looks like it's moving a little faster than my other one did. Okay, so this one came through at 188 megabytes a second. This is good. So this was a good transfer speed. Jetstream 2, I believe, has all SSD hard drives, so things move faster. Okay, I've moved the leaf detection. I'm going to copy the path to the other one. I'm going to do iget k-p-v. And now I'm going to do this npz file. It's only 560 megs. Okay, and it moved to 127 megabytes a second. Maybe for fun, we can see who got the fastest transfer speed, but 188 megabytes per second is pretty good. And I do an ls command, and I can see now that both of these sample data sets we want to use for today are in my home folder work TrAC train 2022. You guys are welcome to put your files wherever you want. Okay, I'm gonna copy paste this command into the chat for anyone that wants to try to reuse this. And remember that you need to do the init command to connect to Cybers first. So let's do this together, and then I need to see some thumbs up or thumbs down for people that are struggling. Okay, so Jody got an error. So I'm gonna do this again. So we type in init. Actually, let me do this. I'm gonna go into. So what you guys should see the first time you run this, I'm gonna edit my iRods config so it looks similar to what you guys are seeing. Just remove it. So the first time you run init, it should just ask you for your Cybers username and password. Because I destroyed that file, I have to do data.cybers.org. The port number, which is 1247. The iRods username. So this is your Cybers username. The iRods zone, which is iPlant. You guys shouldn't have to type this in. I just have to do it because I destroyed my environment. And then your password. And then you can check this as being successful by doing ILS. And it should list just your home directory. Jody, how's it going? Are you having any more success or more failures? Okay. Aditya, could we open a breakout room?
Yeah.
So let's open a breakout room, and then we can have anyone that's having trouble drop into that breakout room, and then we can do some share screen in there, and I'll try to walk people through this. So I think the good news is that I'm about 10 minutes ahead of schedule. So let's, is this a long break coming up? Do we have a lunch break or something?
No, I have the demo and then the lunch break.
Okay. So let's go to our break early right now. Let's get that breakout room open, and then I can drop in there for the next 15 minutes. And then when we come back at the top of the hour, Aditya is going to take over and begin some of the lessons for the rest of the workshop.
Yep. I have created a room, so it's room 3, I think, and by default, everyone is in room 1.
I am not.
Of course. Participants. How do I apply this?
How about now?
Yes.
Okay, so
Okay.
let's see. Okay, so I init.
And then are you using your Cyverse password? Just to,
I am.
Okay. That's your Cybers username.
Yep.
So let's try this. So let's do a RM and then a space and then the tilde / dot irods / oops, that's okay, / irods, and then try a tab and it should autocomplete. Okay, so let's remove that. And then
Okay. So press enter.
Yeah, enter. And then let's do I init again. And yep, that's right. T, enter. Okay, data.cybers.org. And then 1247. And then your username. And then I plant. Oh wait, you know what? Okay, and then let's put in your password. I just had a thought, but yeah, go ahead and put in your Cybers password. Okay, let's go open a new browser tab and go to de.cybers.org.
Aditya, when will be resuming?
At 12,
Okay, thank you.
8 minutes.
Okay, so I asked the folks that didn't need help to come back over here, Aditya. So there's
Okay.
a few people that are going to stay in there with Edwin.
Okay.
It looks like most of us have come back.
Okay. So do I get started, or I can probably wait for a couple of minutes?
Let's wait one more minute,
Yeah.
but they should be headed back this way.
Okay, sounds good.
It looks like everybody's back.
Yeah, pretty much. All right, I think we can get started because again, we have a lunch break at 1, and we have some good amount of stuff to cover. So for this part of the tutorial, we'll be basically using the same Jupyter Notebook, which you guys have access to, Jupyter Hub, and in the schedule, you would see that there's a link to the Jupyter Notebooks here. If you click on that, it opens up this. So as Tyson was saying earlier, so we can actually maintain a lot of version control and all using GitHub. And for that, what we can do is we'll probably we'll clone this repository, which has the notebooks, and work in the repository itself, so that we have all the notebooks we need, and then we can work around. So I just went from the ls to the work folder. So I'm in the work folder, and then I just have to do git clone and then paste the git repository here. And so that should give me this folder. So again I can come back here. If I go inside notebook, so let's go to part 1, and first we'll go to the training part. So here you'll see that there is the Ipython notebook, which we'll be using here. So most of you guys have already downloaded these two data sets earlier when Tyson was showing, but since I cleared my instance, so this I'll have to run this again. So that should. Oh,
It looks like you probably need to go into the terminal and set your password the first time.
Yeah, I did that. Okay. Now let's see if this works.
Should work in the notebook. And the notebook may not show you the progressive output.
It does, actually.
Good.
So in this notebook, what we'll be doing is basically an image classification of a sample of leaves. Basically, you take in a set of images of leaves and identify whether it is diseased or it is healthy. And further, in the disease, there are different categories. For example, it can be because of iron deficiency or because of a low water or different reasons. So for each of those categories are given different names, and for the we'll be doing a classification of given a leaf, what class does it belong to, whether it is diseased, what kind of a disease is it, or whether it is healthy or not. So that's the problem we are looking at. Let's see, there's some okay. So in terms of the data set, so we do have, again, if I go back here and show you the data set. So we do have a big data set of almost around 19,000 or 13,000 or so images. That is this 10 gigabytes of data set which Tyson was downloading earlier. But in terms of performing some preliminary pre-processing and all, we are going to use this small set for doing the pre-processing. Once the pre-processing is done and we have the data set, that processed data set is stored in this NPZ file, which we will eventually use. So just for the sake of the tutorial, I have divided this data set into two parts. One is a small set of original data so that we can look at how we do the pre-processing, and then load the total complete data set of all the processed images. So that's what we are going to do. So again, for those who are facing a space issue, you probably are downloading the complete data set of this plant disease detection. Instead, you need to download the small set, and I think that with that it should be fine. Let me know if you face the issue further as well. So once you have this tar.gc, it's a compressed data set available, then we can extract the images. And once we do that, you'll see a folder here, leaf images. So in here, you can see that there are different classes. So each of them are one category. And then in each of them, you can see there's an output folder. And in that output folder, you have a lot of images stored inside. So this is one particular example. I think this is iodine deficiency. I don't remember which class it belongs to, but it is one of the diseased classes. And then I think 3 is healthy, as far as I know. Yeah, this is healthy. So once you have this data, one thing you will notice is that each of them are of different shape, and they're very high resolution as well. So when we want to train the deep learning model, we wouldn't use the same high resolution images, and we'll perform some kind of pre-processing to generate more data. So that's one thing we would be doing first. So for that, before we get started, I think I also have this step of removing the tar.gz file so that there's no space constraints when we are running stuff later on. I think we are here. Okay. So once we are here, we start importing some basic packages. So in terms of packages, we'll in the beginning use native Python packages, and then some other non-deep learning based packages like NumPy, SciPy, and all, NumPy, Pandas, Matplotlib, and CV2 for performing some image related things, and then image processing things. And then we have Torch and PyTorch Lightning and Torch Vision and all, which are more for deep learning related tasks. So before I go further, let me close the breakout rooms and remove that. I had a survey I thought we could have. So I just wanted to have a brief idea on how familiar you are about deep neural networks. Do I need to go into what it is and all those things so that we can have a good idea when I'm covering through this tutorial? So I'll probably wait for a couple of minutes and then see. 1 minute.
Oh, I have a question about the Jupyter
Yes.
notebook.
Yeah.
So when I try to open it, the notebook file, it says that it's forbidden. So there's like no kernel.
So you are so when you open it from here, it says that no kernel available. Is that
Yes.
what you're saying? So you can select the kernel here, right? So you can select the kernel and select Python 3. Do you
Yeah,
see
when I
this?
select that, it still says it's forbidden. Or the other message was there's no space on the device.
Okay.
So
Let's
which
let's reopen a breakout room. I'll go in there with you and let's look at it.
okay.
I'm gonna go into can people self-assign themselves into room 3?
I don't know.
Let's see. Oh wait, we're all assigned to room 1. So I'm gonna open these rooms, but don't go into them unless you need to go into one. So I've opened the room. I'm gonna go into room 1, and we can go look at this together.
Yeah. So looks like pretty much most of you know what deep learning is. So and there are a couple of people who are who have very minimal information. Let me end this poll. And, okay, sounds good. So in terms of what deep learning is and all, I'll probably go through a little bit as I keep going on through the workbook. If you have any questions, feel free to ask questions, and I think Bernard here or someone here would be able to answer those questions. I see there's a question here from Yash saying, do I have to upload the notebooks from GitHub? You'll have to download it from there. So that's what we did earlier. So I did a git clone of that repository and I got it. If you don't want to clone the whole repository, there's another option. You can go to the notebook here, and when you open this notebook here, you can right click, copy the link, and you can come back here and then say wget and paste that link, and that should give you the notebook as well. So this is another way you could access it. All right, so I'll probably get started further from here. So I do have some helper functions here, if you will, about on basically given an original image, how do I crop it to the center? And then how do I rotate the image so that I can, these are some things I'm not using it here, but I just have it here in case we would want to do some kind of data augmentation. So data augmentation is nothing but you're rotating the original image or some kind of a like you're transforming the images to get more samples. So for example, here we just have 13,000 samples, but 13,000 samples may not be sufficient for you to train a very good model. So for that reason, we can perform some data augmentation by doing this rotation, transformation, different kinds of transformation, and you can even do random shifts and other things and all. So that's something we'll probably not do here, but I just have those in case you want to do that, take a look at it later on. And again, once we come here, so we do have the data stored. So let me take a step back. Training. So you have the leaf images here, and the categories, if you can see here, there's 1, 3, 4, 5, 6, 7, and 8. So that's what I'm giving here as an input, data directory and the categories. And just for the sake of visualizing one of the samples, basically what I'm doing is I'm going to the first category, and in the first category, I'm getting the list of all the images in that. And from that list of all images, I am choosing the first image, loading it using CV2. Okay, there's a comment on increasing the font. It's too big, I guess. Is this okay? You can give a thumbs up if you have any issues, or if you don't have any issues. Okay, let's see. Okay, so yeah. Now, so once you have the like we are visualizing this one particular image, so visualization of one sample. So I was talking about how you're loading from one image. You're loading one image using CV2 and then converting it from BGR format to RGB format. So BGR is basically blue, green, and red, and then we are converting it to RGB. That will give us better visualization of the images. So that's what we are doing here. So CV2 loads it in BGR format, so we have to do that conversion when we are plotting it using Matplotlib. So, sorry, I must have missed some steps here. So there you go. So I'm able to visualize one sample. So if you can see, I can actually print out what's the shape of this image. So it says that it's 1018 times 722 pixels of size. And this is not the high resolution image which we would be using for our deep learning model. So for that, what we are doing is we are choosing an image size. Right now, the image size I'm choosing is 128, and I'm going to resize all my images to 128 times 128. That's the image size I'd be using. So for that, I'm just saying cv2.resize, and then that's there you go. So I get this image, and this is the new array. So I can even do a new print new array dot shape, and that should give you what the size of it is. So for generating the whole data set, basically, I can perform the crop to center and rotating the image and other operations. But for now, I'm refraining from that. I'm just going to resize all the images to one particular shape, and I'm also collecting all the classification numbers so that I can use it later on as well. So for this, what I'm doing is I'm going to iterate through all the data directories I have and the path which we would be using, and then from there we'll be doing the training and all. So while this is going on, do you guys have any questions you want to ask, or is everything working fine for you guys?
Hi, Joe. We were in the breakout room, so we missed a few things. Could you please repeat again?
Yeah, so I was just explaining about like loading the data. So after importing the packages and everything, I have few helper functions for performing some data processing. For example, you would want to crop the images to the center and you want to do some random shifting and all for generating more data, like for performing data augmentation so that you have more samples and you can augment to your original data set for better learning. So those are some of these functions we have over here. And we have the whole data set in this dot leaf images folder here. And so dot slash is basically current directory, and then the leaf images folder inside it. So this notebook is running from here. So you go inside the leaf images, and then there are 7 of these categories: 1, 3, 4, 5, 7, and 8. And for those categories, we just visualize one particular sample using matplotlib. And then we are resizing for this case, particular tutorial, I'm just going to resize and not do any other data processing on the images. So that's what I'm doing here. So the original image is of 1018 times 722 image size, and I'm resizing them to 128 times 128. And that's what I'm doing here. And after I'm doing that, basically I am creating the whole data set of a pair with both the input image and the class number as well, which is the category which I would want to train on. Okay. There's a question on why resize to a smaller image size, 128 times 128. That is because the larger your image size, the learning becomes difficult, and the larger the image size, your model needs to become more larger, and you need a lot more GPU memory and CPU memory and all those. I mean, we'll talk about those things later on as well. So there's something, yeah, so that's an answer to your question as well. Yeah. Any other questions? Yes, so that's a very good question. What information got tossed away during resizing? One, we are subsampling from the original image. So for example, here you have a lot more features of the small edges and all, which are smudged, and you're losing a lot of those fine grained features. That's one thing. And then another thing is you're losing the aspect ratio as well. So here it's a rectangular image, which you're making it a bit square looking over here. So in some learning problems, this could be an issue, especially when you're dealing with these problems in engineering. Then you wouldn't want the images to be squished in, and you don't want to lose your aspect ratio. So in that case, you will choose an appropriate aspect ratio and resize your images according to that. And there's a question, but wouldn't changing the size abstract away some information? Yes, that's correct. So that's where the trade-off comes. Are we really gaining anything additionally by giving more like image size? For example, if I try to learn this disease detection problem from, say, a 16 by 16 image, then these features of the color, yellow color, and then the rotten edges may all get smudged away, and I wouldn't be able to do any prediction. But compared to here, if you look at it, you're still preserving the features when you're subsampling to a smaller size. So that is the key thing which we need to take care when we are doing these kinds of data processing and all for deep learning, that you want to preserve the features which you want to learn. At the same time, you don't want to make it too difficult for it to learn as well. Okay, so in terms of why too difficult and all, I'll probably talk about when I'm going to the deep learning architectures, because that's when we will talk about the different layers and how each of them get affected by the size and everything and all. Okay, any other questions? Right, so we have the data loaded. So, and then, as I said, these images were just for showing you how to do the data processing and all. Just as saying, as it goes in the deep learning, or in general, people usually say this, that a deep learning project, 80% of the time you spend is in pre-processing the data and 20% in the learning. So right now I'm just showing you a very simple example of how to do some data pre-processing. But as people who would be actively working in deep learning, most of your time would go in just doing the data pre-processing and all. And yes, so yeah, there's a question on why did I have to write the functions. There are some existing libraries already which do that. Yes, that's correct. But these sometimes you may not want to use the exact same functionality as what the existing libraries do. For example, some of the functions may be slightly different because for if you, I mean, maybe not in this case, but in other image cases, I know that all the possible data augmentations need not work for your particular data set. So in this case, it does. So we could use the existing libraries. But just as a demonstration, I just wanted to show you how you can use those data augmentation libraries. Like you can write your own data augmentation libraries as well. Any other questions? So as I was saying, we also have a tar.mpz file. So what I did was, in order to save some time and to have the tutorial run for the whole data set, I did this for the complete data set of all the 13,000 images, and I saved it as a NPZ file. And that is the NPZ file which I shared with you guys. So this NPZ file, leaf disease detection.npz, is something we'll be using to go forward in the rest of the tutorial. So essentially, whatever total data you had over here, I'm just going to replace that with whatever the complete data set I have. And then for training, and I am going to divide the data into 0.6% or 60% of training and 20% validation and 20% testing. So the idea is that I will be using 60% of the data for training and 20% of the data, the validation data, for actually performing some hyperparameter tuning. And this hyperparameter tuning will help me in identifying the best particular model. So what is the best neural network architecture, or what are the best parameters which would be conducive for my training. And then from I will finally perform a testing where I will evaluate whether the model is really performing well for a general data set. That's the testing data set. So I'm splitting the whole complete data set into these three categories. So after I split it, you can see that I am using around 8,300 images for, or 8,300 samples for training, 2,700 for testing, validation, and 2,700 for testing as well. And once I have the train, validation, and test data, I can go ahead and clear up the memory of the total data set as well. So I just need the train data, val data, and test data for doing any of the operations. So any questions so far? Because now from now onwards, I'll be going into some specific things you would need to do for running things in PyTorch.
I'm still confused. The purpose of validation data and test data separately, because both of this data, the training, the model is not seeing it while training, right?
Yes, but you are seeing it and you are taking a biased decision of using the model which is performing best for the validation data, right? So when you're doing the hyperparameter tuning, you are seeing that this model performs best for the validation data. Just because it works well for the training data and the validation data doesn't mean that it should still work for the test data. And that is the generalizability part of it. You want to ensure that it still generalizes for not just the training data and the validation data, but also for the test data. Is that clear?
Yeah, okay, that helps. Thanks.
Yeah. So that's the data splitting part and all. So now comes the part where we want to do something for our custom data set. So we have our data set created here. Now, PyTorch has this abstract classes called torch.utils.data.dataset, where you can create a dataset class. And this dataset class helps us in maneuvering through a lot of data processing steps. At the same time, you can even perform some on-the-fly data augmentation and other things when you need it. So the thing we are doing here is basically you send in this data which you have created and whatever transformations you want to perform, and then you can store them during the initialization. And then you have few functions called len and then the get item, and these help you in getting access to those data. So I'll probably explain these two things as with one particular example. So what I'm going to do is I'm just going to run this code block. So that's going to execute that. And then I will create this train dataset and val dataset instances where I'm sending in the train data and I'm sending in one particular transform, which is just transforming to a particular tensor. And then I have the val data and the test data as well, which I'm instantiating. Let me create another code block here. So what I'm interested is that when I want to finally get one particular instance of a set of samples, then what I do is I just say train data set of 0, and that's going to give me a tuple. This tuple is going to be the image and the corresponding label. Okay, so what that is, so if I do image comma label is equal to this, so it's giving me that. And how is this doing that? So this 0 is this double underscore get item method, which takes in the index. And for this index, it processes the information and gives me whatever I want. So it gives me both the input and the label, processing all those things, and gives me at once. So this is something which is useful for performing your own custom data set and custom data processing. In fact, I think someone pointed out earlier about existing libraries for performing these operations. Yes, you can. There are some transforms which you can use here. So transform.toTensor I'm doing here. You can even do a random shift and random crop and all those things here as well. So those are the transforms which you can use straightforward. These are all given in Torch Vision, and we are using those. And this length is nothing but going to give me the length of my data set. So for example, if I say print length of train data set, it's going to give me the length of that data set, which is 8302, which is nothing but self.n samples, which I'm returning over here. Okay. Any questions? Okay. So once we have instantiated the dataset classes and all, the next thing we'll do is basically use a deep neural network model. As I was explaining earlier, so deep neural network models are basically a set of layers stacked together for giving you one particular output. So if I want to quickly annotate and show something, so basically you have an image over here, and then you can assume that you have a set of neuron layers which are processing the information in some way and giving you the final output of what the class is. So this is your image X, and this is your what you're predicting Y. So each layer can easily be represented in a vectorized format as y is equal to wx plus b times some nonlinear transformation, sigma, some nonlinear activation function and all. So depending on what layers you're using. So if you're using a dense layer, then that would be something which is just doing a fully connected layer. So what that means is basically you flatten the whole image into a fully connected vector. And using this fully connected vector, you are connecting to another fully connected vector where you are making all possible connections. And these connections, what that means is basically, so say this is x1, x2, x3, and so on. And then say this is y1. Then y1 can be written as some w11x1 plus w12x2, and so on. So basically, it's a fully all kinds of weighted connections are made from each node in the input to another node in the next layer. And you have several such layers. So if you don't want to perform such fully connected connections, then other possible option is that you can use some convolution operations where you are taking the weighted sum of all the values inside one particular kernel and get one output, and then you move this filter all along all along for getting the fully next output basically. So I'm just not going to spend too much time explaining what deep neural networks are and everything, but the idea is that a deep neural network has a set of layers which you are going to use, and you stack them all together to form one particular architecture. And there are several neural network architectures which are used as standard because they are known to perform well for these particular tasks. So for example, in this particular case, it's an object detection or an object recognition task where you are detecting whether there is a particular particular category of disease in the leaf exists or not. So for this particular task, ResNet 18 or VGG 16 and several other standard models exist. So these models, most of these models are already available in Torch Vision library, which we have imported earlier. So this library is what we are using for these standard models. So for example, here for classification, you have all these different models which you could use. And same way, if you go further for say some quantized models or even semantic segmentation, for example. So semantic segmentation has a few other models which you can use. And then object detection, instant segmentation and all has a few other standard models which one could use. So in this case, let me go back to the notebook I had. So in this case, I'm using a ResNet 18 with and I'm passing in the number of classes to be equal to the length of the categories which we had earlier. And that's how I'm getting this model. Okay. So this particular model, and once you have the model and the data, you have to define the training algorithm. How do you train this, the model and all, right? For doing that, I am using PyTorch Lightning. It's another package which does all the orchestration of how to train the model. So initially, the weights of your network are random weights, and you are going to tune it using some optimization libraries like SGD or Adam or some of these different optimization algorithms. And these optimization algorithms are what are orchestrated using PyTorch Lightning. So the way it works is for initialization, I'm passing in the information of what is the network and all the data sets, the train data set, the val data set, and the test data set. And then I'm also defining what the loss function of my model is. So for example, initially when your model takes in some random weights and then you're transforming, it gives you one final output. And you want to ensure that this output is correct. So you have the label and you want to ensure that your output is equal to the label. And how do you ensure that? You compute a loss. In this case, the loss function is a cross entropy loss. And this loss function is going to help me in training my model better. And I also need to keep into account what are the metrics of how do I ensure whether the model is working well or not, right? And that is done by this torch metrics.accuracy. And once I have this defined, I need to define what is my forward pass going to look like. What forward pass means is basically what am I sending as an input, and how does my network process it? And my network is going to take in the input and then predict this. In case if you want to do some other operations, then you can do those additional operations in this forward pass. And now you need to define what you want to do for a particular training step. So in a training step, so basically the idea of this is that, so if I want to annotate here, so you have the whole data set. Say I can put that data set in a like a chunk form. So you have 8,000 training samples, right? So what you do is those 8,000 samples are made into smaller chunks of say a batch size of say whatever batch size you want. And each batch is used for performing stochastic gradient descent or some optimization. So basically what that means is you have something called as a loop over all these batches. So you have for loop of all the batches, and in each batch you'll basically perform the forward pass, which is this self.forward. So you're getting the batch of data, and that batch has all the images and the target labels corresponding to it. And for that forward pass, you get what the predicted value is. This is nothing but the forward computation of the network. And from this forward computation of the network, you get the predicted value. Then you now compare the predicted value with whatever the target value should be. That's this loss value. And once you get the loss value, so you get loss L from the forward pass of I'm just going to denote that as f of x. So you get the loss function, loss value given this thing, and then some weights which you are tuning. So you get this. Once you get that, you return that loss. And what that's going to do is it's going to do something called as back propagation. That is the way you get dou L over dou W, which is the gradient of the loss value, which you're evaluating here with respect to the weights. And once you get this gradient, you can now perform the back propagation step. And once you perform the back propagation step, you have the losses and all defined, and you can perform the optimization. And the way the optimization is done is basically using this configure optimizers. So you're configuring what optimizer are you going to use for performing the optimization. And that's the optimization part. So once you define the training step, similarly, you'll have to define what is a validation step. So again, the loop which we had, so you had a like for loop of all the batches. And once you have the for loop of batches, you can now perform for loop on the validation batches. And once you perform this operation of for loop on validation batches, then we can later on even go to a test step, and we can perform testing as well. But testing is something we won't do during the training process itself. So, but before that, basically you perform the training on all the batches, and then you perform inference on these validation batches. And you do this for a set of epochs. Okay, one epoch is basically one pass through all the data. So for, and here you'll have some epochs for which you train the model. And you do this several times for for the loss to reduce and have some kind of convergence in the trends and all. So that's something which goes on. Same way, you need to define what your test step is going to look like so that you can perform a final test of your model, evaluation and everything. Same way, if in the future, when you want to perform a prediction of from your model, then that is something you do with the predict step. And we also need to create a data loader. A data loader is basically going to take in that torch data set, which we created earlier, and split it into batches for us to use the batch wise stochastic gradient descent, which we discussed earlier. So the batch splitting into batches is done using this train data loader, val data loader, and test data loader and all. So this is the whole framework of what all is needed for you to perform the training. Okay, so it basically under the hood does all the things which we need to do, but you just need to define what all parameters you want to control. So once you do that, so now I can instantiate that class by sending the classifier with the model, the train data set, val data set, and the test data set, and I get the PyTorch Lightning model. Sorry, I must have missed that step. So now once we have the PL model, now we can do the training, and the training is done by instantiating something called as a trainer. And the trainer is where you provide information of what GPUs do you want to use. And if you want to, so when you're performing these operations of whether you are learning or not, whether it is converging or not, and all those things, you define some callbacks such as early stopping. Early stopping is going to basically, if your loss, the validation loss, is not improving much, then you can stop the training right there and then not proceed further. That's one way to ensure that your model is converged in terms of what is the best performance it could give. And then you can also have some logging. You can log the information, and the logging can be done using a Tensorboard logger or a CSV. You can store it in a local CSV file as well. And you can even save the checkpoints as the training is progressing. So that's the checkpoints part. And then you can even do profiling of how the training is going to be performed and all. So that's something we do. So we instantiate this trainer. And now we can, once we have, when I instantiate, I ask for GPU 0. So I said, I'm going to use the only GPU which I have, which is the GPU 0. So that's what it says. So it says that GPU available, and I'm using the GPUs. And I say trainer.fit PL model. So note that I'm running this for 10 epochs. So this is once I execute this, it's going to start the training process. So while the training starts, I have some time to answer any questions if you have. So feel free to ask any questions right now. So as you can see, the training is proceeding further, and then the loss value is trying to reduce further. Of course, there's some noise in the loss and all, but yeah. So once the epoch is complete, it performs. So one epoch is complete, then it performs the validation, and then it goes to the next epoch.
Aditya, I have just like a question. Does it seem like this A100 is any faster or different than a GTX or whatever on a normal workstation?
Yes, it is slightly faster than the GTX in a workstation. But then in terms of, I mean, here this problem is probably a bit small. So right. It's obviously fast, but yeah, there is a significant speed improvement of using A100s.
Good.
So while this is running, I can show you something. So I have also done some Tensorboard logging, right? So here's where I can show you some thing which we can do. So I can go to the folder where I'm running that, which would be notebooks, part 1. Sorry, CD training. And then I can do Tensorboard. And then log dir, and then give plan detection. Sorry, it's logged and / plan detection. And this should start a Tensorboard session. This is basically a server where it is going to, you can visualize the results as it comes. So this is something which is very useful when you want to see how the model is performing as you go forward. So the way you do that is basically, it says it is hosting the Tensorboard server on port 6006. So since we are all running in a VM virtual environment, and we are doing everything in the TrAC train, this Jupyter hub, the way you can access this local port in here is basically, so right now you see that I'm in TrAC train 14.cybers.org, and then user Aditya Balu, which is my name. So I can copy that, open another tab, and then say proxy / 6006. Is that the, yeah, 6006, and then a slash, and you enter. Then you will see that there is a thing which you like it, the Tensorboard session will show up. And this is how you can keep track of whether the training is happening well or not. And you can keep track of all those things. And right now I'm just running one case. So you just see version 0, but if you are running, say, several cases, then you can store all the versions here as well.
Aditya, can you go back to your Jupyter lab? And then on the left side, there's the little GPU icon down right there. Yeah. And I think that, I don't know, can we try the memory or the utilization rate, and we'll see if it shows anything. Is it still running, or did it finish?
No, it's still running.
Okay.
Oh,
So
it finished actually.
Okay. So yeah, those little icons, that's like an NVIDIA dashboard that I installed, and I don't know how useful they are. But
yeah, they are useful in terms of finding out whether the GPU is being utilized or not. So for example, if I put this model for training again, then you can see whether did it run?
Something happened.
Try that again. There you go. So it's training. So you can see that it's using almost 40% of the GPUs basically, and yeah, 3.3 gigs of memory.
Yeah. Okay. Yeah. And I wonder, there might be a way to do the Tensorboard inside the lab, but I think that other proxy is a little bit better to look at.
Right. So this is, I mean, yeah, you can always do over there as well. Visual Studio Code has some plugin to actually do it inside itself, but this is something we can use for, in general, how to access any ports, whatever you want. All right, so now that we have performed the training, we can perform the test as well. So let me stop this training which we had, and then we can say trainer.test, and it's going to run the test and give me finally saying this is the profile of how much time it took and all. It will say, okay, because I stopped the model training in between, so it says the test accuracy is around 29% and the test loss is 1.8. So I think I'll stop here and then probably start after the lunch break, because there's some part of deployment and other things which I wanted to cover, but I don't think 4 minutes is sufficient to do that. So yeah, let's stop here and then touch base at again 2 o'clock Central Time. Meanwhile, I can answer questions if you have any, or put it on chat, or we can, yeah, answer them.
So is the accuracy here, which is approximately 0.3, empirically a good accuracy in this kind of problem?
No, it's not. We have a very good accuracy of around 89 or 90 to 95% or so. I don't remember the number, but it's above 90%, which we had got earlier. So it's one particular instance where we are just stopping the training much earlier, and we are not performing any data augmentation or anything here. So it's a very naive example just to start and show you how things work out.
Thank you. And the second question is, when dividing the data into test, training, test, and validation, so under what circumstances would you consider to do cross-validation?
So when you have very small sample space, particularly if you have, say, 1,000 samples, then a cross-validation, a k-fold cross-validation, where you are performing these repeated experiments of dividing it into k batches and then switching it and all. That's done when you have very small data set, because you cannot ensure that your whatever small subset of data you're using is representative of the whole data space. Only when you have a very large data set, you can assume that it is all independently identically distributed. So the 20% of the data is representative of what the whole data set is going to look like. So that's the criterion of when to use cross-validation and when to use this splitting strategy we are using here.
Gotcha. Thank you.
Could I make a request?
Yeah.
Can we take a class picture before we go to lunch?
Oh, yeah, sure. So
if you're still at your computer, maybe turn on your camera so we can do a screenshot. So we're using Jetstream 2. Jetstream 2 is not publicly available yet. It's in this early production. And we want to be able to highlight this to the Jetstream 2 people this week, just to say thank you. And hopefully next time they'll give us a lot more resources to run this workshop on. And we're not going to go to lunch until everyone turns their camera on. And if you don't want to turn on your camera, there's if you have the newer version of Zoom, you can do an avatar. So you can be a rabbit or a cat or a cow. Well, half of us with cameras on. That's probably good enough. All right, I took a screenshot, so I'm good.
sounds good. Yeah. So we can assemble back at 2 o'clock after 1 hour, and then it gets going from the next part.
Yeah, I have one.
Yes.
So when I do the GitHub cron, right? So
Yes.
after point, and so I check back the database, and it won't able to show what I clone from the GitHub.
Did you can you check which part, like which folder did you clone it in? It would be in the folder where you like wherever the path of your where you are.
Yeah, I just clone to the work, right? I just clone to the work directory,
Okay.
but so I'm able to see the just now follow like the tutorial. I create the folder, but I cannot see where I clone. Like, yeah, it's not showing.
So it's not showing in the file explorer, is what you're saying?
It's not showing in the data, like, because when I check from the like, I check from the like the data from the. So I when I check, like when I you can share, like when I check the personal data, so
Okay.
I won't be able to see where I come from the GitHub. Yeah.
Okay, so probably we can go to a breakout room and then probably look at it.
Sure.
Let me put you in room 3 and then I can come there and see. I Yes, Jisai, can you share your screen? Hello? I cannot hear you. Oh, so I don't know if are you able to speak now?
Yeah. Yes. You see, if I.
See, you can here you are able to see.
Yeah. For example, if I connect
Yes.
like from here, correct? So in
Yes.
my work directory,
Yes.
and then from here, city work. So from here, I can see where I come.
Yes.
But from the data set here, the data like I
Yeah, so
cannot
that's because you are running this. So this is not you're running this in the local. So this /work is in this local VM. You have not pushed this, or you have not done a I put or I get from the iRods data center. Basically, this is all in your local this local VM which you're running.
So you are seeing this part I'm running is in the local.
Yes.
But I like even it's in the local, correct? I clone the like GitHub, correct? It's supposed to download to the local, correct?
It has to. Git clone is going to download it to your local.
Yeah.
Yeah. So it is downloaded, right?
Okay. So how I just like how would you check where it is? Like then I got a little bit confused.
So you double click on TrAC Train 2022 in the left.
Yeah, here it
books.
shows, right? So
Yeah.
how should I upload it? Because originally I was in the 05 and then some like somehow got forbidden. So they switched me a node to 15.
Okay.
And when I was in the 05, when I connected, when I doing the GitHub clone, so it actually like show in my working directory both of the file I created in the data. So for this case,
no, it didn't show you both the data. It showed you this folder only. How will you show it show both the data?
It showed like originally it showed both.
Okay, so whatever data you created in TrAC Train 5 is not accessible here. Is that what your question is?
So my question is like, if now, correct, I clone this, how should I upload this to the data?
You need to do an I put. So right now, if you look at the notebook which I sent you, the training notebook, there is a I get command, right? So there you need to do a I put and put the data in the data folder.
So you mean
So you have iget on top.
Yeah.
Iget is getting the data from the Soionomics folder. So now you need
Yes.
to do iput and send it to your home.
So I need to get the entire folder to send to my home.
Iput, not iget.
I
Yes.
put to my
Yes.
this entire like directory to
Yes.
the
Yes.
home. Okay.
Yes.
Sure.
Okay.
Okay. Yeah. Thank you.